All right, okay, without further ado, Ryan, yay!
Hey, thank you. So now, any of you may leave, but I will be deeply hurt. And no, don't leave it. We'll leave whenever you want. So I'm here to give a talk about how to swim. So we're going to start with breaststroke. No, sorry. First introductions, I guess. Hi, I'm Ryan. I do this every talk. I'm a community-focused software engineer working at Bluetail. I help organise Code Bar Birmingham, where we will be running a session probably in 2 weeks, but I don't exactly know the day because I never set it up. But it's really good to have a look at it. I have a really unhealthy obsession with programming mascots for some reason, and I probably own a calendar, which is a real in-joke that you would know if you were at .NET user group about 3 or 4 months ago. And, cue this being the wrong talk. Oh, no. I'm here to do a talk on you. We need some drums here. We need some drums, if somebody could do the table. Oh, that's right. Scalable, weekly, consistent infection style process group membership protocol. Who's excited? Woo! Let's go. Oh, God. So, but please don't leave the room just just hearing that name. It's a bit, oh God, what's this going to be? It's more interesting than it sounds. I must promise. I'm not sure if I'm going. Also, all of the slides for this were literally written today because I went through the talk this morning and went, I don't really like that. And I just deleted the entire thing. So if there are errors within the slides, I am sorry. So, Chapter 1. I aim to make this as well broadly accessible as possible. So it'll begin picking up in pace, but we'll begin with the basics. But before I start, has anyone actually used or heard of Swim before this, in terms of things?
I looked up 30 seconds of work today.
Haha! Esoteric protocols, let's go! So, this is a computer. Yes, it's a computer. We're all in agreement that this is a computer. Yes. Cool. But it's a bit lonely. What happens if this computer had some friends? Woo! They're now all kind of just sitting there, not really doing much, to be honest. But how about we started to make them talk? How do computers talk? And I'm literally doing this slide by slide as it lags. They talk with packets, which are like little individual boxes of information that you push down the line. They look a bit like this. They go, to my dearest, 192.168.1.1. Some data, kindest regards, 192.168.1.2. Where these are internet protocol addresses which just represent a computer on a network for those who aren't aware of that. There is some more stuff that goes into it, but for the sake of this, that's all that you really need to know. And there are 2 ways of delivering these packets. You have UDP, or User Dendrogram Protocol, or Transmission Control Protocol. I like to think of these as, if I press the button, it should go over, it did not. Okay, I'm consigned to walking over here and pressing the laptop a million times. One's every, which is where they will probably boot your package, drop kick it, and then maybe it might reach your destination sometimes. Whereas Transfer Control Protocol is DPD next day delivery, signed, it's all insured, and if your packet goes missing, they'll send another one for you. And how do the packets get where they need to go? Well, you might have seen one of these lovely pieces of equipment before in your life, I hope, maybe, everyone in the room, right? Which is a switch. You can think of it as, it's a switch where multiple computers can talk to each other with these packets. And together they make a local area network, which is, you can think of as like having a mail depot where the mail is being routed to a central location and then from that central depot being routed back out to certain houses or addresses. And for further afield, we have the internet, which is just a lot of routers in various different places and at various different scales that do this. And that is what we call a wide area network. And this is like shipping internationally also. I just realized that mouse is going to be really annoying. Where your mail gets where it needs to go eventually, but it's got a lot of hops, a lot of different stops. So, it works out in the end though, doesn't it? So, now that we're kind of all on the same page about vaguely how the internet works and packets are swapped between computers. By the way, stop me at any time if you do have questions. I love questions, especially when midway through the talk, and I don't. That sounded really facetious. It isn't. I do. But yeah, Swim. What does it mean and what is it for? Well, we've got effectively 4 different terms that I'm pretty sure the original authors of the paper just desperately tried to mangle so that they could get swim as its name. But I will run you through what these mean at a time when they become relevant. So process group membership protocol is effectively when I've got a certain collection of computers, how do those computers know, firstly, which other computers are on the network, and secondarily, which of those computers are healthy? Think of it a bit like, as I'm saying that, think of it a bit like a Facebook chat where you've got all of your besties, which are all bestie one because I couldn't be bothered to custom write the slide more, with people available to chat to, but you want to keep a list of who's willing to talk, but also who's online and not gonna just ghost you if you send them messages. So how this conventionally works is going out and finding new computers in your area. You just get a printing press, all right? You start printing loads and loads and loads and loads of bits of mail, and you go to insert IP address here. What's sending me this talk to, well, something about B2B sales also exists, so please note that I exist. From yours truly, 192.168.1.1. And you wrap it all up and you lob them onto the internet, and some computers within the network might get that information. This is known as IP multicast in terms of a computational sense, but it's kind of like a hack in the sense of not many places support it. It's effectively something that has to be enabled in most places. It's not like it just comes out the box, which isn't really ideal, but we'll get on to the replacement. And part 2 is knowing who's online. So you have a checklist, but how are you going to, question whether people are online or not? Well, you just get your printing press again, of course. And you just go to whomever, ping, from 192.168.1.1. You write a bunch of these letters, and then you add a little tear-off form at the bottom that says, just return to me an acknowledgement that you've received this letter, and I'll note that you are, in fact, alive. Yes, very good. So we lob those emails out, and, well, so those letters or packets or whatever you want to call them. Some of them go, yep, we're okay. Some of them are like, what? No, I never received this message. You get back the acknowledgements of those messages, and then the ones that you don't get acknowledgement from, you just get rid of. You're like, all right, they don't exist for me. You're dead to me. Oh, single tear. And off they go, leaving you with a list of clients that you know are healthy and alive because they have sent you an acknowledgement. But just hearing this initially, does anyone in the audience have any thoughts about possible problems with this style of approach?
How do you discover devices that you haven't seen before?
Don't worry about it. So typically in this model, when a computer joins a network, it will multicast out onto the network, I'm here, hello, and then all of the other computers will begin pinging it. And when it gets pinged, it can note that IP address down, and it eventually can results in a system state where everyone kind of knows everyone else just through shouting at each other, hopefully. But still, yeah, what's up, Callum?
If someone was to start injecting code into servers and all that sort of stuff, that cause issues.
Probably not on this tier because it's just ping and pongs. It's just, here's a bit of data, here's something back, nothing to protocol area. Yes?
You don't know who is actually offline and who just hasn't received your message.
Yes, and also, and I think this is the biggest, or the biggest one to me, I am going to be the only one who's going to be sending out messages to all of my closest friends. And when you've got a lot of servers, oh, well, everyone gets a printing press now. You get a printing press, and you get a printing press, and you, and oh no. Yes, the network can just become very much overloaded with the sheer amount of network traffic if you're constantly pinging everyone, which leads us on to demo 1, the problem, where I actually show you this, but I really do hope that this works. So I'm the sort of person who spends all of their time just like building visualizations for protocols, because why not? We want all for the ping approach. We want pings, we want acknowledgements, and let's not have any packet loss for now. Okay, well, let's add a node. Ooh, node ID 1. This is a computer. By the way, can you see that all? It is a bit small, I think. All good?
No, it's good.
Yeah,
I
okay.
can see it.
Yeah, okay. So we have 2 nodes, that's fine, all right, yeah. 3 nodes, all right, we'll just begin sending pings to everyone. 4 nodes. Ooh, this is fine. Oh, there's a bit of traffic there. 5 nodes. Oh no, let's just add some more. And the network grinds to a halt because that's an insane amount of traffic to just know whether somebody's awake, alive, and or asleep. And if we add enough nodes, this simulation falls apart and it begins lagging like hell. So yeah, let's not do that. But we still want to know who our peers are and we still want to know if they're healthy. The other problem, which I will get to, and I will refresh this before it crashes my computer, thank you, is, all right, let's see if this reconnects. I'm going to do this every time I do a demo and see how long this lasts for. And I will also move the mouse for you. And, oh, the first mistake, I think that's a duplicate slide. Or am I just going back? Am I going backwards here? Is this going, how did I go backwards? Okay, there we are. Oh, how Swim fixes this, the start of chapter 3. Well, it's scalable, which is nice. Scalable in this sense means instead of just picking up a printing press and lobbing as many letters as we can at anybody and anyone who's willing to take our mass marketing campaigns, we instead take a bit more of a mediated approach. We grab a quill and ink and we very carefully, very lovingly, to my most important 192.168.1.2, ping. Yours sincerely. We take a lot more care in the messages that we take a lot more care in the messages that we send, and we send them in such a way where we round robin them. So effectively, we send a ping to the first person on our list and get an acknowledgement back. Cool. The next cycle, or the next ping interval, we ping the next person and get an acknowledgement back. We ping the next person and, oh no, the message has disappeared in transit. And after a certain amount of time of going, have you gotten back to me? No, you haven't. We get rid of the computer from our list and continue on as normal to the next client and ping and round robin and so on. There's the second error. I tried to fix that, but it didn't save, so mixed up brackets. So that fixes issues with network traffic in the sense that now every network or every node is only sending 1 packet of data every ping interval instead of like 5, or well, n number, because it's however many nodes that you've got in the cluster, which it can be very, very, very quickly scale up, as you saw before. It's also pretty brutal in the sense that you've got a chance to respond. If you don't respond, you're off, gone. I don't care about you anymore, you're dead to me. So what if instead we do something called a ping request, where if we can't make contact with a node, we ask a random number of other nodes that we do actually know are healthy, or well, we think are healthy, hey, can you get in contact with 192.168.1.4 for me, because they're not on the network. You create a few of these, as I said, 3 or 4. You bind them up in a message. So you ping a dead target. The target's like, all right, no, I'm gone. You then create some more messages, send them out to some other computers that you know on the network and go, hey, can you ping them instead? And if there's an acknowledgement back from them, the acknowledgement will go back to these computers and then over to this computer where it will then go, all right, ping acknowledgement passed. But in the case where it doesn't, then once again, it will do a multicast across the network shouting, this node is dead. And all of the other computers will go like, all right, sure, we'll strike that off our list as well. And effectively, the computer has left the network because we've tried. And this is the main failure detector for the swim protocol, which I don't know what these slides are, where we do demo 2, which is me just going back to the other tab because I built this as well and I spent too much time on it, so you're forced to watch. So I will add, let's say, 4 nodes. Oh, wait a second, this is spoilers. No, you can't do that. Oh, no, no. That's for later in the talk. Be gone. Okay, you saw nothing. I will set it to dissemination approach, multicast, ping approach, round robin. We have a ping request. Well, we'll just deal with that.
Did you code all this, right?
Yes, I did. It was fun. It was fun. It was me sitting there for about 4 days straight reading that paper and going, oh God, there are some details that are just not defined and I've got to use my creativity for this. No! Ah! But I will go through it in more detail. You can see the multicast joins there. So what I'm going to do is I'm going to add a partition. Ooh. Anything that goes through this line is now lost. Oh no. By the way, can you actually all see that? Because that is really small. I can zoom in. I'll zoom in. Ooh. The problem is this requires a mouse wheel. Oh, there we are. So you'll see that there'll be pings and pongs going across. But I think the main one that we care about is if I filter to ping request, you'll see that the node 2 and node 1 are able to keep in communication with each other pretty much in perpetuity, even though there's no direct line of connection through, because they're just repeatedly going, all right, I can't get a ping from you, so I will instead send a ping request over and take that as acknowledgement instead. So you can see them diverting traffic through all of these nodes. And it's not every node on the network. You just take a random sample of 2 or 3. That is all configurable as part of the protocol. And I think that's it in terms of that part of the demo. So I will refresh this so I don't get my laptop lagged again. And we shall go back. Oh my God, I've gone through a lot of the slides already. Oh, this might be a very quick talk. Or not, we'll be fine, we'll be fine. It gets a lot more complicated very quickly, which is pretty ideal. But I'll try my best to explain it. So, everyone gossips. And this is where the really interesting part of the protocol comes into play. So currently, we've been using IP multicast to disseminate information. So effectively, this node's dead, this node's alive, and we've been shouting it across the network in a barely supported sense, and it doesn't really work too well anyway, to be honest. So what else can we do? Well, how about we just start sharing rumors in that case? And this is where the protocol gets really interesting. So, do you know before when we had this thing where it's like, to my most important, ping, yours sincerely, something, kindly tear off this acknowledgement. Well, it's kind of empty, isn't it? It's literally just a ping. It's just like, here's a poke, but the size of the ping packet is actually quite big. You know, you've got a lot of space here, before and after, and you can actually sneak information into a ping packet and use that to start sharing state across the system through rumors. Ooh. Like this, ooh, but rumor 1, rumor 2, rumor 3. Well, what rumors do we have? Oh no, this is known as piggybacking, by the way, if you want to read the paper for some reason, you pain-inducing people. So what sort of rumors can we spread? Well, we've got 2 in the baseline for Swim. We've got the node is alive, or the computer is alive, so we've gotten a successful ping response, and the computer is dead. What starts the rumors? So a rumor starts for when a node is alive, when you get a successful ping response. So if you've sent off a ping, you're getting acknowledgement back, you can then start spreading a rumor saying, I think that this node is in fact alive. And in a similar way, if you want to start spreading a rumor about a node being dead, you go effectively after a certain timeout, when you've had no response from a node, you go, ooh, the node is dead. And I shall start spreading a rumor for that. We can play a game of rumor top trumps because, of course, you can have conflicting rumors on the network. Some nodes might be going, this node is dead, and others might be going, this node is alive. And you need a way of reconciling how important a rumor is to take heed of in order to properly spread them. So rumors about a node being dead always trump rumors about a node being alive. So if they're on the network for any reason, a single node says, that's it, this node is gone, it will spread across the network rather quickly, and the node will be ejected from the network as part of the protocol. And you want to spread the hottest gossip. You don't want all last week's rumors. Oh, Sally did that. No. You want the hot stuff fresh off the press. So you keep account of how many times you've shared each rumor that you've seen, and if that rumor, and then you effectively order the rumors that you have by most shared to least shared, and you share the least shared first, incrementing every time that you share. So you've always trying to keep the most recent information on the network if you can, given you've got a finite amount of chances to share information with your ping and pong requests. It's not like you're just lobbing this out to everyone. So you'll go like, oh yes, this is the one to share because it's green and good and has only been shared 5 times instead of 10 times. And also, you aim to share the rumors about evenly. So if you've got rumors about things being dead and rumors about things being alive, you normally have 2 pools of rumors that you pick from. And you go, well, in the paper, it says that this is how they would implement it, but not, that's actually part of the protocol. Well, it's about a 50-50 split between alive and dead rumors in terms of this node's dead, this node's alive. So you also want to stop sending fake news. So if you're spreading information about a rumor being, or you're like, this node is alive, and then a conflicting ping comes in where a rumor says this node is dead, you start immediately sharing that the node is dead as a rumor. Instead, so it effectively displaces other rumors that you are currently spreading. They're mutually exclusive. You can't share multiple rumors about a node at the same time. And this is what you do if you hear a rumor. If you hear that a node is alive, if it's a new computer that you've never heard from before, you add it to your list of things to ping, and you can just randomly ping it. Also, if you get a ping from an unknown peer, you add it to the list of things to ping. So,
So what about a ping from a computer that you were told was dead?
No, this is a problem with the protocol, which I'll get back to. Because realistically, what you're supposed to do if it's a node that you think that's dead, you store the fact that you know that it was dead and you reject it from coming onto the network. You keep it off the network until it cycles. Or normally what you would do is you would allocate like a universally unique identifier of some kind. That doesn't really represent the node itself, so it effectively comes in as a new node instead of as an old one, because an old one should be rejected as per the protocol. Yep.
But if you were told that the node is dead, if another computer says that the node is actually alive, would that...
This comes back to top trump. So you hear that the node is alive, you've already heard the rumor that it's dead, you ignore the rumor that it's alive, you just reject it.
Yeah.
It just bounces off you.
But if it's the other way around, then the fact that it's dead trumps.
Yeah, you go, all right, I know that it's dead. I don't care about it being alive anymore. I'm just going to start screaming from the heavens that it's dead to everybody that I ping from now on. And it effectively spreads very quickly the fact that a node is either alive or dead on this network. Pardon?
Telling everyone I'm dead. Sometimes I can still hear his voice.
He's going to get there. Yep, that's it.
Couldn't that become a denial of service?
In
That's actually what I was going to go with.
terms of...
In terms of if you had a bad node on the network going, everyone's dead.
Oh yeah, it is a...
Everyone's dead.
Yeah. Everybody starts screaming, oh my god, it's dead.
Collapse the network, basically.
Yeah. This is built for internal trusted networks of nodes. There are things that you can do to protect against this that I will get onto later.
So you're saying chronology doesn't matter. If it's dead before it's alive, it's dead. And if it's alive before it's
Yeah, there's no timing to this. It's just it's alive or it's dead. It's a binary state. And if it's dead, you shout that it's dead. If it's alive, you shout that it's alive, unless one becomes more than the other.
Is there a particular reason why the fact that it's dead trumps the fact that it's alive? Or is that something you're...
It's confusing.
Yeah, because once a node has been declared dead by a single peer, the state of the network can get very messy very quickly if you don't boot it from the network as quickly as possible, in the sense of it's not there's no way that a node can go from dead to being alive, like consistently. at least in this rendition of the protocol. The next rendition I can let you know more about soon, which does actually give nodes the chance to speak back when they have been falsely claimed of being dead, which is not very nice. Any other questions about this so far? I know it's a bit of a thing, but...
Oh, I have a question.
Oh, yes.
I'm
Down here.
Hello.
I was wondering, so in a trusted network, what is the value of knowing which computers are alive?
This is a peer-to-peer protocol, so there's no way of knowing what other... Because effectively, what you want to do is you want to know all of the peers in the network, but you don't necessarily know any more than one peer to begin with. So you effectively join the network, say, I'm joining, hello, and from that, eventually, which is why it's weakly consistent, you'll eventually get all other healthy nodes within the cluster ongoing. It's kind of like a peer-to-peer thing. Yeah, what's up?
Peer-to-peer, we only know one other person in the network. How on earth is it a trusted network?
There are, this is, for reference, this is a protocol from 1999, and it has been very, very, very heavily expended with a huge number of modifications since to make it viable for production use nowadays. And I will go through those extensions later, but this is kind of the chronology of the SWIM protocol more than the final form of the SWIM protocol. Its power level is over 9,000. It's something. What's it called?
So more that, I suppose these sorts of things like peer-to-peer, they're also used in games and that as well. So for example, Left 4 Dead uses things like peer-to-peer between normal players and the server. Is it a bit along those lines?
Yeah, in terms of you've got computers directly speaking to other computers without some central managing computer or server saying, you do that, and you keep a connection with me, and I'll relay everything through myself. It's a very distributed way of dealing with it. Anything else? Or I can... Callum.
But then obviously in the comparison with protocols, you have things like servers, clients. The server itself, if there's any changes on the client, it won't actually change it on the server.
Yeah, in server authoritative game models, they do have it where the server effectively normally runs like a full simulation of the game, and you just feed it inputs. It goes like, oh, I pressed the up button, and then you go, all right, you press the up button, cool, I'm going to move your character, and then you can puppeteer it across. So it's fully trusted in the sense that the game server has all of the control. Whereas with a peer-to-peer network, it is a lot more complicated normally, but you can do stuff around it like full determinism, which I can maybe do at the end of the talk if you're all interested, or we could talk about it after. We should be good. Anyone else? Nope, cool. If you hear that a node is dead, you get rid of it from your ping list, you never ping it again. You remove any rumors about it being alive from your internal list, which I think we've already said, and you spread the rumor of it being dead. You go, this node is dead, quick! Get rid of it. So bringing everything together, gossip is shared with every ping and acknowledgement. It is no more traffic than you already have with a standard ping ACK model of a kind of, how do you put it, process group membership protocol thing. Rumors are selected based on how modern they are or how new they are, but I think this is quite an important point, is how new they are to you, not how new the actual rumor itself is. So if you're very late in receiving a and it doesn't matter, you still spread it like it's new gossip because you haven't seen it before. Death rumors always replace alive rumors, and replaced rumors stop being shared once the new one starts being shared. So effectively, something's alive, something's dead, you stop sharing it being alive, it's now dead. Which we can do. Oh, the SWIM protocol. Oh, I thought I was going to do a demo here. Hold on a second. That's, yeah. Oh, no, okay, no, I remember this. Okay. So we've got two other words here. I think I already raised it. Weakly consistent, which is the middle, the w in SWIM, is effectively eventually all clients within a network will converge on a single state and normally the correct state of the system. So everyone will eventually know who everyone else is, but not immediately. You can have half of the network not know who a node is until much, much later, but eventually they should all ultimately know who a person is. Which means that every node has a different list of IP addresses that they internally maintain until they see new information. An infection style is the way that stuff spreads. So it spreads like an epidemic. And actually, it was really interesting in the original paper. They did a lot of the mathematics that they did in terms of how fastly you could disseminate this information was through epidemiology, not through standard like computer science stuff. It's kind of the study of how nodes infect other nodes with ideas is really cool. Which is why I did a talk on this protocol, which leads us to demo 4, which is spreading gossip. And now I can finally show it you. Don't look at that. Spoilers. Gossip. Who knows who? Round robin. Round robin? Round robin. I think that's probably fine. All right, so we'll start adding some nodes, loads and loads and loads of nodes. And eventually, we can see the rumors starting to spread about nodes becoming alive. These green lines effectively represent rumors that this node 14 is alive. And you can see that as things go on, you know, oh, look, everybody now knows in the network that I'm alive because you're just sharing it through pings. This might be really hard to read, so I will zoom in a bit. But effectively, you have this kind of thing here where you have rumors being spread. The A's stand for alive, the D's stand for dead, so don't worry about that. Also, I do have a UDP simulation on here, which I will turn off, so you can start losing random amounts of network traffic to see how a network can fare when it's 20% network traffic drop or 50% or whatever. Anyway, let's turn the node off. Node 0 is now dead. Oh no, that's not ideal. So everybody in this, look, node 8 never even got the memo that node 0 was alive, but we'll see. Eventually, things will start screaming about this node being dead, and we will see it very quickly converge on, oh, no, everyone thinks that you suck, so get off. Oh, there we are. The rumors are spreading, it's dead, it's dead, it's dead, it's dead. And if it tries to come back online now, it gets booted because it's like, no, sorry, you've been confirmed dead, so you can't come back online. And now everyone's just screaming that 0's dead. And that's roughly how the base implementation of Swim works. Any further questions on that before I move on to complicate it even more because, you know. Ooh, pardon?
How does it rejoin once it's declared dead?
Normally with a new ID. So you go like, all right, I am no longer this computer, but I am a completely different computer that looks very suspiciously the same as the last one. But once again, protocol from 1999, so it has improved a lot since.
So this is a solution to the broadcast, which basically crashed the computer.
Yeah, because it's effectively serving the same purpose without because you can see here, this is quite a few nodes. That's not huge amounts of network traffic. And I could just mash this. I could just go like, more nodes, more nodes, more nodes, more. And it's a lot, you know, there's stuff happening, but it's not exactly like, you know, it's not completely out of control. This is effectively, for every node that you have on the network, you have one more packet going every ping cycle, which is a lot nicer than n more. Yeah, factorial. I think it's factorial or something. It will. If I change this to ping approach all, I think it would crash the browsing tab. So I'm not going to do that. But for reference on how that works. Anyway, I'm going to go on to the last part of the Swim protocol, at least as it was written in the paper, which is ready. You need a drum roll for this. Proper drum roll. Oh. Wait, no, oh, for God's sake, I've got tabs in the side. Okay, never mind. That was just a hype for nothing because I thought the tab was coming up as well. So there are some problems with the Swim protocol. Mainly, I think as we raised earlier, if a computer has been declared dead, it's like, yeah, that's it, you're gone. You booted off the network, which really isn't ideal. Especially in some circumstances where you know, some nodes might just have flaky internet, or whatever, or you know, you want to have a time where you've got a lot of chances to check whether a node's alive before really committing to it being alive or dead. So what can be done? Let's start the Among Us protocol. Sorry, I meant the suspicion subprotocol. Which is the same as the Gossip protocol. So this is an extension to the protocol that we already have, but with a few more components that make it a bit more stable in terms of working out whether a node is alive or dead. And this does get a bit more complex, but hopefully we should all be able to follow along at home and do ask questions as I raise it. So we have a new rumor type, which is the SOS rumor type. Effectively, you're checking whether a node is suspicious or not. It follows the same underlying governing rules, but it effectively replaces the role of the old death rumor. So instead of if you don't get a response for a ping and then a subsequent ping request, so the failure detector triggers, you start spreading a rumor that a node is suspicious. Something wrong about that node, not sure what, but very suspicious node. And it effectively takes the place of, oh my god, the node's dead, just get rid of it from the network. And the dead state still fulfills the same role in the sense of once a death rumor has been started, it can't be stopped, it just rolls across the network and it gets booted. But this is where things get interesting. So when you receive a suspicion rumor, you start a timer. You go like, stopwatch, click. All right, I'm waiting. And what you do is you keep pinging the node, you keep it on your list, you don't get rid of it, you act like it's alive, but you just sit there and you run down this timer. And if that timer runs out before a death message has come in for you, or before a death message has, oh no, sorry, no. If no conflicting rumors appear about it being alive, and that timer runs out, you start screaming that it's dead. And once that's happened, that's the final state of the node, it's gone from the network. Objection! I'm right here. I'm alive. Thank you very much. Why would you spread suspicion about me? That's not very nice. So, if you receive a suspicion rumor about yourself, you effectively start a super alive rumor, which is done by incrementing something called an incarnation number. Yay, protocol specifics. But effectively, what this allows you to do, and you start spreading that rumor to the hill, and this alive rumor supersedes the suspicion, and the fact that you have actually come back online will propagate across the network, and hopefully everyone who's suspicious of you will go, all right, I'll just forget about it. No timers, no nothing. Yeah, what's up?
Will it trump a death rumor?
No. Once a death rumor has been started, it's gone. You're out.
So it's an intermediate stage.
Yeah, it's an intermediate stage where effectively it's a race between you getting this traffic about you being alive out before someone kills you. Which is why you want this infection to spread quickly, and why you want to distribute at ratio. You want to say, I'm alive, is like really important. Which is why you want the newest stuff spread first. You always want a constant stream of new information. You can actually like overload the protocol if you have too much traffic going on at once, and then you just have one node sitting there that's suspicious of another node. It's just not getting that alive rumor. It will just start a death rumor, and then it will be kicked from the network. At least from my own implementation. But yes, so not all rumors are created equal. So one saying that this is alive, but it's got an incarnation number of 1, is counted as a lesser rumor to if the incarnation number is 2. And I think a very important point to note is only the node in question can increment its own incarnation number. So it will go like, all right, I'm refuting this, I'm increasing my incarnation number, and I'm going to say that I'm alive on incarnation number 2, which resets all of the suspicions for incarnation number 1. And why that's important is because effectively, you've got this chain of incarnation numbers where you can have multiple, like, all right, I'm alive, oh, I've crapped out of the network a bit, so suspicions have been started about me. I'm now refuting that. And then, oh no, actually, I'm suspicious again because another node couldn't make contact with me. So I need to increment it again to keep myself alive. So it's effectively, every time you see a suspicion about you with a node counter less than you. Yeah, what's up?
Sorry. What's to stop a different computer from saying, hi, I'm definitely the suspicious IP address and I'm going to implement this number?
It's the same as internal attacks where if you wanted to do that, you might as well just scream death to all of the computers and they'd just all collapse from the network. Once again, this assumes a fully trusted system, which... What's up?
Is there a limit on the incarnation numbers that I think?
No, it can just keep on counting. So if you've got a really flaky node that just goes down, up, down, up, down, up, down, up, down. I mean, I think, to be fair, there probably is like a physical limit in terms of the amount, the number that you can keep on a pack, like the number that you can actually fit into the packets, but that's not discussed in the paper.
If that number went above that moment, but it started overwriting more important bits in the packet?
Whoever wrote the protocol, I don't think really cared about the packet limits beyond more. It's more of a theoretical thing in the sense of. And it was 1999.
Was this also 1999 or was it later?
This was 1999. This is all from the original paper.
Oh, okay.
And to be fair, if something's been that inconsistent that it's hit that limit, you probably want to kill it.
Yeah, you might want to boot it or something. I'm not sure. It's. Yeah.
What would happen if there were no limit? Someone else kick it off if it keeps incrementing itself.
What would happen if? I can't think of the right words here. You deliberately increase a number from more than one.
In terms of like 5 million.
Talking about viruses back then, internally.
Once again, the protocol assumes a trusted network, so it doesn't really make cases for that. In the sense of there are a lot of things that this is a very bad protocol if you want to keep it secure. In terms of it's not a secure protocol. This is pre-HTTPS. This is like no encryption whatsoever. I will get to you though on the encryption side of it, which is later on. Unfortunately, I didn't have time to actually implement or write that, which I was wanting to do, but lots of tumultuous stuff. Anyway, so there's now a new pecking order effectively. So you've got bottom of the rung incarnation number 1, this node is alive. This node is suspicious. This node is alive with a higher incarnation number, blah, 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 so on and so forth. Effectively, if you see a higher incarnation number and it's alive, then a lesser suspicious one, then you effectively accept the alive rumor. Otherwise, you accept the suspicion rumor. You always prefer suspicion over alive for the same incarnation number. And then, even if your incarnation number is infinity, if you're dead, you're dead. You're like, boot, booted from the network. So bringing that all together, the suspicion protocol adds effectively this grace period where loads of nodes on the network can activate their failure detectors. It's all configurable as part of the protocol, where effectively maybe 5 or 6 pings will come to you in the time that you're down. And in that time, 50 or like 20 or 30 nodes have been asked to try and reach you, and they haven't, because it's just random chance whether you get hit or not. So you've been asked an awful lot of times whether you're alive, and you're not. If you come online at any stage, you can immediately refute, and the network will go back to just thinking that you're okay. And yeah, you need to handle more cases in the sense that you've got suspicions and dead, and you want to share at the same ratio. It's the final damage. Sorry. So we'll go back to this blob of stuff. I can finally show you it in its default settings. So I will add a node. I will add a second node. I'll add a third node, and this is going to fail horrendously, hilariously, because I coded this directly to the spec and haven't actually properly Actually, no. You know what you can do is you can do this. You can then set that value, and then you can let it go really quickly and let it just spread rumors about everything being alive, so I can clear the network from that state. Give it a bit, the alives will disappear. Come on. Come on. Come on. We should be seeing mostly pings and acts. All right, pretty much all ping acts now. We can slow down. Because now we've got a network where most of the nodes pretty much know who everyone else is. I mean, you can see in the cases there are like certain nodes that don't know other nodes. It's not a perfect system, but through random chance, they will eventually get pinged by other said node. You don't have a state where like one node doesn't know another node. And oh yeah, that's an important distinction. You only spread an alive rumor about a node that you didn't already know about in terms of starting it up, so that you keep the network clear of constants. Oh, this is alive, this is alive, this is alive. Otherwise, you won't get the important rumors. So sorry, I missed that off the original thing, but you only start an alive rumor if it's a new node that you've never met before. Anyway, now we can start with some suspicion. Which node should die? Which node? Should we do 29 or 0? Maybe 20. 20, yeah, 21. 21. Every time, I've got you. All right, so that's now faulty. So the failure detectors are going to start screaming, and you will begin to see lots of traffic trying to get to it. And a suspicion has started. It's propagated across the network. Everybody is now very suspicious of that node. But, it's alive. Wow. And the network goes, oh my God, it's alive. And you can see the rumor fighting it out. And eventually it drops off, apart from this node watching you. Yeah. So the node's gone back to a system where it thinks that it's healthy. And for reference, the green here is all of the nodes that think that node 21 is healthy. All of the orange is the ones that suspect that it's dead. If I go back to node 21 and just let it die, so we just like keep it there, and I'll actually filter into the ping axe here. So you'll begin to see more and more things will start asking it, are you alive, 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 are you alive? Are you alive, are you alive, are you alive, are you alive, are you alive? And look at all of this traffic. All of these are chances for it to return in. And it's like ping request, ping request, ping request. It keeps on getting poked. It's really, really just not saying anything. Come on, do it. Ping, 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 ping. It's had like 1 million pings at this stage, and it's still not responding because it's like a faulty boy. And I will speed up time a bit here because I think I set this to like some long value. Oh, fast. Oh, there we are. Everyone thinks that it's dead, but I lost the traffic because I had it filtered. No, there we are. Everyone's screaming, it's dead, it's dead. And the node has been booted from the network, sadly. So that's the swim protocol with the failure detector. Oh, sorry, with the suspicion sub-protocol included in it. And that is the end of the paper when it comes to that thing that you saw at the moment. Wasn't that more interesting than you thought? You'll be like, oh, boring, oh, blah, 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 blah. That's a pretty cool protocol. I really do like it. There are some limitations, and I'm sorry I didn't have time to properly write this in, but there are some other things. It is quite slow to converge sometimes in the sense that nodes don't always know what other nodes are saying. It doesn't really offer to share information. It's not like an information sharing protocol. It's just maintaining a list of like IP addresses. And islands can form in larger network partitions. So if you have like, this is data center A and this is data center B, and the network switch between them explodes, you can have 2 isolated islands and they can't reconnect because everyone in island A thinks that island B is dead and everyone in island B thinks that island A is dead. And it's not all nodes are like created equal in the sense of the suspicion times can be, well, you'd want to be configurable in some cases. For instance, chunky database node that takes like 10 minutes to spin up, you really don't want going down unless you're absolutely dead certain it's gone. Versus some random ephemeral task that's just like, all right, I've gone. It's like, oh, who cares? Yeah, just go. Couple of seconds. Also, it has no encryption. And I can talk about the extensions that have been made in the questions. I'm coming just in a sec. But first, who uses Swim, or at least the extended version of it? The main people are HashiCorp, who maintain a library called Surf, which is like a pure implementation of Swim, and then Swim with a bunch of extensions bolted onto it, which is what I was referring to earlier, that allow for stuff like synchronous key encryption with key rings and all sorts of wacky stuff and verifiable proofs of who's sending is saying what they are actually saying. And this also runs most of Roblox Callum. Callum, it runs Roblox. This is used for Roblox because Roblox is Hashi Stack, so you're like that. Anyway, it's the final demo. Sorry. Yeah, I did say that was the final demo. That's not exactly the final demo, but I'll see. Oh God, gimme. I will see if I can do this very quickly, but if not, don't worry about it. Oh God, you stop it, all right. So if I go out full screen and I go to this non-suspicious project called GoPot that if you were here before you would have heard about. But GoPot uses the Swim protocol. So if I do docker that, it will go, the Docker system daemon has not started. Or it will give me a lot of terminal spam. Or it will do nothing. Hello? Hello? That's very, doesn't normally hang. Huh. Maybe it's just being slow. You know what? I'm going to go to my... Oh, hey, there we are. Oh, it's having... Oh, no, splitting out my stuff. So I've got 15 nodes of a particular service that if you want to read up on it, it's very funny. It's called GoPot. I did a talk about it at Foster, but you can see, sorry. And we have a thing called members list, which is their swim protocol implementation. Effectively talking about nodes being alive and dead. So let's just go into the Docker control panel here, go to dashboard, and we've got a cluster of like 15 nodes running. So I just like stop one because I feel like it. We can see that nodes will start screaming, oh, I'm suspicious of that, and then getting down to prove that this actually is a real protocol instead of me just drawing lines on the graph. Node 8, be gone. So node 8 has crashed, and hopefully we'll start seeing some traffic about, oh, eek, 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 look at that. Sync failed, sync failed, sync failed. Suspicious, no axe. Suspect timeout reach, peer booted from the entire network. Ta-da! So it does actually do what it says that it does. Anyway, that is at least the end of the talk where I talk your ear off, but I will also say, there is a really cool tech conference going on in Birmingham that I'm helping organising that I will now shill, called Tech Mids, which should be very developer focused and has a lot of really good speakers looking at the CFP internally at the moment. We will be announcing loads of speakers. It's at conf.techmids.org, not .io. There is a .io domain. We can't get it because the old organisers won't give it to us. So should be good. Should be good. Really exciting. It's the 14th of November all day. So it's a Friday. Should be fun. And it's at the Everyman Cinema in Birmingham.
Oh, yeah.
Yeah. Anyway. Further reading. Thank you very much. There's some further reading. Anyone want to take pictures? Further reading here? No? Oh, you've got 5, 4,
They know enough now.
3.
We're not supposed to memorise that?
Oh, no. Well, if you want a picture, you can take 5, 3, 2, 1. All right, you've all got a picture. You've all got a picture. If you want a picture, no. But this is really cool. This is really cool.
Oh yeah.
And finally, any questions? Woo!
Any other questions? Jonathan?
Could the swim, you were talking about encryption with it, has anyone ever tried, could it be done with zero trust implementations?
No idea.
Seems like a logical...
I think so. From what I'm aware, it does, it says a symmetric key. So it uses symmetric key encryption, and it just has a key ring that just cycles through keys, and you've got to propagate the key updates. I think you can propagate the key updates through Swim, through the extended version of Swim if you want to, or you can just do a centralized key server or like vault.
Some interesting papers on kind of zero trust protocols where you basically do. Everyone knows the full secret, but you only share certain parts of it so that the secret doesn't actually get shared.
Is it a bit like a secret sharing scheme?
I can't remember the name of it. I was at a cryptography conference.
Where you like split up a secret into multiple parts and then like divvy them out amongst
a
certain
number of
Harry Potter approach. You basically prove that you know the secret by computating a problem.
Oh, okay. That's interesting.
Yeah, I was wondering if Thank you.
Any further questions? Oh, sorry, Ryan.
I know.
How is this different from ARP?
I'm aware of ARP, but I'm not sure what ARP is. It might be a very similar protocol. It might be another extension of it, to be honest.
Yeah, that's a good question.
Swim is kind of like the like grandfather protocol in terms of like, this is HTTP 0.0.0.0.1, and everyone took it as kind of an inspiration for how to build an entire class of protocols on top of it, and extended versions and modified versions. So.
That's really cool.
Yeah, I was just going to say, I guess ARP would be a layer 2 protocol where this is dealing kind of in a layer 4 space.
Okay.
For the OSI
Oh, a different
model.
layer.
Yeah, it might be because this is PingAC. This is purely like ping pong responses. There is no kind of higher level function to it. There is actually an extension in the Surf version of Swim where it like syncs data like through TCP channels at a much higher rate, so convergence is way quicker. And when you actually join the network, you just go, I'm joining, and then it's like a node says, all right, you give him your entire list, or a few nodes give him your entire list and merge it. So they basically get a full list of IP addresses straight off the bat just from joining. So there's a
Cool.
few
We have
extras
time
to it.
for one more question.
One more.
One
Make it
more
count.
if there- Yeah.
Yes.
I've got a joke about UDP. I tell you, but you wouldn't get it.
Every time! Every time!
That's really good. Yeah.
Thank you so much again, Ryan.